Section 4, AIC Matrix Generation. First, we're going to talk about theory of Uncity Aerodynamic Panel Method. And the highest fidelity flow equation is the Navier-Stokes equation. And if we assume the flow to be inviscid, we can reduce the Navier-Stokes equation to the Euler equations. Further, if we assume the flow to be irrotational, and we can reduce the Euler equation to the full potential equation. And and the Navier-Stokes equation and Euler equation have 5 flow variables, but the full potential equation only has one unknown, which is velocity potential. If we further to assume that the wing is a thin wing, then we can further reduce the full potential to a transonic small disturbance equation. From the Navier-Stokes equation to the transonic small disturbance equation, and they are all nonlinear equations. So even to solve the transonic small disturbance equation requires some sort of CFD approach. And if we further assume the structure oscillation amplitude to be small, and we can reduce the transonic small disturbance equation to the unsteady time linearized small disturbance equation, and this equation is a linearized equation, but with varying coefficients. Those varying coefficients is the steady flow variable. Okay. And if we further assume there's no transonic shock, and we can finally we can reduce to a linear potential equation, and this linear potential equation has a surface integral solution, and then we can discretize the configuration into many small panels, and we call a panel model. Then, for subsonic flow, we use zone 6. For sonic flow, we use ZSAT. For supersonic flow, we use zone 7 to solve this linear potential equation on the panel model. Okay, for unsteady time linearized small disturbance equation, and its solution has a surface integral which is identical to the integral equation of the linear potential equation, plus it has a volume integral. So in order to solve the volume integral, we have to put a volume cell around the panel model. Then the varying coefficient is the steady flow solution. So we import the steady flow solution from either Navier-Stokes solver or Euler solver, and we interpolate the CFD solution in the flow field to the centroid of the volume cell. Then we can solve this unsteady time linearized small disturbance equation using Z-Trin. And finally, if we inject the so-called rotationality correction to the zone 7 method, then we have a zone 7U for hypersonic flow. And showing here, this equation is the so-called transonic small disturbance equation, TSD equation, where the capital V is the total velocity potential, and beta is the square root of 1 minus free stream Mach number squared. And if we split the total velocity potential into a steady potential phi naught plus unsteady velocity potential due to harmonic motion, so it becomes e to the IKT, and then we further assume the unsteady potential is much smaller than the steady potential, because we assume the structural oscillation amplitude to be small. And so if we plug this equation into the TSD equation, we can split TSD equation into 2 equations. The first one is the steady TSD equation. The second one is unsteady time linearized TST equation. And because this is a linearized equation with respect to time, and then we can apply Fourier transform to transform the time-dependent term to the frequency domain. And on the right-hand side of this equation, sigma v consists of phi naught x. Phi naught x is the steady perturbation velocity. This is defined here as the steady background flow. So this is a linearized equation, but with varying coefficients. And this varying coefficients and in Z-Tran is provided by the high fidelity CFD solver, like a Navier solver or Euler solver. Therefore, in Z-Tran, we do not solve the steady TST equation. We rely on externally provided high fidelity CFD solution. And for this equation, and it has integral solutions. So for the point at x naught, y naught, z naught, and the velocity potential consists of 3 parts. The first one is a surface integral, and you integrate this integral around the surface of the configuration plus the wake surface, where delta phi in the steady sense is doublet. Partial phi, partial n in the steady sense is called source singularity. The second integral is a volume integral, and so we have to solve the integral in the flow field. The third integral is a surface integral, integrate around the shock surface. If we assume the steady perturbation velocity is small, in other words, the phi naught x is very small, thereby sigma v is small, and then we have this linear unsteady panel method. In other words, we assume sigma v to be small, to be 0. So we only have this surface integral, and so this equation is linear unsteady potential equation, and we use the panel method to solve this integral equation, and we can further recast the velocity potential into acceleration potential. So the acceleration potential is delta Cp. Delta Cp is the pressure jump across the surface, and because the wake cannot sustain force, so the delta Cp on the wake surface vanishes. So all we need to do is to integrate this integral around the surface, where partial phi, partial n is a source singularity, g is the unsteady source kernel function, kappa is the unsteady acceleration potential function, and g and k have different expression at different Mach numbers, and so the whole configuration is divided into wing-like component and body-like component. So and we distribute the delta Cp on the wing-like component and the source singularity on the body-like component. And so how do you distinguish the wing-like component and body-like component? Any aerodynamic component whose cross section is of airfoil-like section, and that can be defined as a wing-like component, because the airfoil like section satisfy the Kuda condition, and it become a good lift generator. And the body-like component does not generate that much lift. Okay, so we put a source on the body-like component, and we put the Cp on the wing-like component. Further, because the linear unsteady potential equation does not involve any steady flow turn. Therefore, the thickness and the camber effect does not contribute to the unsteady flow. Therefore, to model the wing-like component, we only put the delta Cp on the main plane of the wing-like component. Therefore, we model the wing-like component as flat plane. And if the body-like components such as fuselage, underwing stall, the body, the missile body, and so on, they are all defined as a body-like component, and we discretize the body-like component into many small quadrilateral boxes called the body boxes, whose leading edge and trailing edge are parallel to the YZ plane. And we put we put a control point on at the center of a body box. The wing-like components are discretized into small trapezoidal boxes called a wing box. And for subsonic flow, we put a control point at 85% core. For the supersonic flow, we put a control point at 95% core. For the sonic flow, we put a control point at 99% core. And then we assume within each panel the source singularity on body box to be constant, and the delta Cp on the wing box to be constant. So we can solve this integral equation, and then the velocity potential at a point x naught y naught z will be equal to the summation of the ki plus unknown delta Cp, and the summation of nb number of body panel times gi times partial phi partial ni. So delta Cp delta partial phi partial n becomes unknown, and so where nw and nb denotes the number of wing boxes and body boxes, where ki we solve this integral equation within a small box, and gi we solve this integral equation within a small box. And so this equation and so the box where the GS control point is located is called the receiving box. So we put a control point on the x naught y naught z naught. It receives the aerodynamic influence coefficients from the sending box. And then we have unsteady boundary condition, and the invisible flow boundary condition require the flow to be tangential to the moving body at all time, can be expressed by this equation, where S is the moving surface, and then we, for arbitrary elastic body in harmonic motion with a given mode H, and so H we can split it into IJK component. So we have Hx, Hy, Hz times e to the IKT, and then the unsteady boundary condition reads the gradient of unsteady velocity potential dot the normal vector of the panel equals Fb. So Fb can be expressed by this equation, where nx, ny, and z are the all normal vector of each panel, and where h where the plan is a differential operator with respect to x, and then hx, hy, hz times ik is the so this is a complex boundary condition, and to understand this boundary condition, let's take the simplest geometry. If we have a flat plane located on the xy plane, So the mode shape we only have one component, the mode along the z direction. So all other terms, because n x n y, they are 0. So we only have nz equal to 1, and then we have a pitch mode, and the pitch mode. So this one, the slope along x represent angle attack. Okay, and this term, if we transform the frequency domain back to the time domain, this term actually represent the hz dot divided by free stream velocity. So this is a velocity induced angle attack. And so if we can further express FB equal to a matrix times HK, and in the HB can be shown by this matrix, where HK, and on each panel we have 6 degrees of freedom, and the first 3 is HX, HY, HZ, and the last three terms are the slope. Okay, so this is in KSAT. So therefore, each panel, each box has 6 degrees of freedom. Then we apply the unsteady boundary condition at all wing and body boxes. So this term is the body box, is an influence at the body control point due to body box. This term is the influence at the wing control point due to body box, and this term is the influence at the body control point due to wing box, and this term is the influence at the wing control point due to wing box. So we have the FB here, and so we can invert this matrix to solve for the unknown source and the delta CP. And so this matrix we call AJJ, and then we can solve for the unsteady aerodynamic forces, and in KSAT, where the AIC is K by K matrix. So the AJJ inverse and times FJK multiplied by a SJK matrix. This SJK matrix is an integration matrix to convert the CP to forces. So each panel has 3 forces and 3 zero moments. So AIC become a K by K matrix. And then we talk about the Zona 6 method. Zona 6 is for subsonic unsteady aerodynamics. It generates the steady and unsteady subsonic aerodynamics for wing body aircraft configuration with external stores and cells, including body weight effect. It can model any combination of planar, non-planar lifting surfaces with arbitrary bodies, including fuselage, store, and thin missile, and so on. And it is based on a high-order panel formulation for lifting surfaces, and this formulation is higher order than the double lattice method. And if we as shown in this example, on a 70-degree delta wing, and if we cut the wing into 40 core-wise boxes and 10 span-wise boxes, and if we look at the CP along span station 2, and both Zona 6 and double lattice result are smooth. However, if we look at the CP along the wing T, and the double lattice solution become highly oscillatory, and this is because double lattice is a lower order panel method. If you look at the National Aeroelastic manual, it says if you use a double lattice method, you have to restrict the panel aspect ratio to be less than 3. Okay, so if you look at the aspect ratio of the boxes along the wing T, its aspect ratio is very high. Therefore, it violates this modeling restriction, and therefore give you this bad solution from the DLN. And we have validated Dongano 6 with many wind tunnel data and many configurations. And showing here is the NLR F5 wing with the underwing tank, pylon, and the tip tank. And showing here are the real part and imagined part CP along the underwing tank, and the open circles are the wind tunnel test data. The solid lines are the Dongano 6 solution. So you can see the Dongano 6 solution agree with the wind tunnel measured CP very well. Now we're going to show the difference between Dongano 6 and the double lattice method. And in 60s, we had a steady low order lifting surface method called vortex lattice method. And in this method, a vortex line is placed along the quarter core on each box. The choice of the quarter core location is inspired by the exact two-dimensional thin airfoil solution. So the success of the vortex lattice method led to its unsteady flow extension, and Urbano and Rodden developed the double lattice method in early 70s. Meanwhile, in the middle of 1970s, Woodward and Pennell further advanced the lifting theory with a fully distributed singularity over the aerodynamic box. In the Woodward's method, a constant pressure or linear doublet distribution is distributed on each box. In Pennell, a linear pressure or quadratic doublet singularity is distributed on each box. Both methods have higher order singularity distributions than the vortex lattice method. And Dongano 6 is an unsteady flow extension of the Woodward method. And this equation is linear steady flow potential flow equation, and this equation is a linear unsteady flow potential flow equation. So both equation has an integral solution, and in terms of the source term and the doublet term for the steady aerodynamics. For unsteady aerodynamics, we have source term and we have a velocity potential term, where r is kind of a distance between the point x, y, z to the control point x naught, y naught, z naught. Okay. If we on the thin wing, we the unsteady steady and unsteady source term vanish. So we only have the doublet and the velocity potential term, and then the doublet term in the steady flow can be converted into vortex, and for unsteady flow, the velocity potential can be converted into the acceleration potential. Both vortex and acceleration potential on the wake are 0. Therefore, we only need to evaluate this integral on the lifting surface only. We don't need to model the wake. And because we need to calculate the velocity components, and so we have to take a gradient of the potential. So once we take the gradient of the potential, and you will find out, and this term, if we take the derivative of 1 over r, this term becomes 1 over r cubed. And because we have another gradient term here, and this one will further increase the order of singularity to 1 over r fifth. And but even we have a two integral, if you take the integration twice, you can reduce 1 over r5 to 1 over r. This is to say, even you can solve this integral analytically, the resulting analytical solution is in terms of 1 over r. So it's singular. So we have to remove this singularity. And so based on the Stokes theorem, we can, for a given doublet distribution, the Stokes theorem can say that this doublet distribution equals a vortex singularity vector plus a ring of vortex. So if you look at this integral, and the order of singularity is 1 over r cubed. So if you integrate this integrand twice, the resulting analytical solution is in the order of r. So it's not singular. However, if you look at the line integral, even you can solve this line integral analytically, the solution still is 1 over r. So the line vortex is singular. And in the pan-airs formulation, it assumes the doublet distribution to be quadratic. Okay. However, they impose the continuity of doublet between two adjacent panels. Because the doublet is continuous, therefore the line vortex between two adjacent panels cancel out. So even the line vortex is singular, they don't have to evaluate the line vortex. However, along the wing tip, because there's no adjacent panel to cancel out the line vortex, you still have a two line vortex, vortexes and along the wing tip. And this line vortex actually is trying to simulate the vortex roll up from the wing tip. So if you look at aircraft doing takeoff, and along the wing tip, it has a roll up vortex. So this line vortex is to simulate those roll up vortex. And in the Woodward's method, the doublet distribution is assumed to be nearly along the chordwise, and it's constant along spanwise. So if you convert the doublet to vortex, so on each panel, the vortex strength is constant, and then because it's constant doublet along the spanwise, therefore you on each strip you have a two line vortex. Okay, and because the doublet is continuous along the chordwise direction, the line vortex between the two adjacent panel, upstream panel and downstream panel, cancel out. Okay, so there's no line vortex, only two line vortex on the right hand side, on the left hand side of each strip. Also, because the pressure difference between upper surface and lower surface is equal to -2 times mu x, and because the delta Cp is 0 on wake, so in Woodward's method we do not need to model the wake because the wake condition is automatically satisfied. And in the vortex lattice method, the doublet is constant on each panel. Now, if you convert to a vortex, because the vortex is kind of a derivative of the doublet, so the vortex becomes 0. All you have is a ring of vortex. And however, rather than placing the line vortex along the leading edge, they in the vortex lattice method, they place line vortex along the cortical, and because the center of pressure on the 2D thin airfoil is at the cortical. Okay, And the vortex lattice method, also the double lattice method, place the line vortex along color core and a control point at 3 color core on each box. And because the 2D steady thin airfoil theory shows that the center of pressure is at the color core. So if you put a single vortex point at color core, and also you put the control point at the 3 color core, you can satisfy the Goddard condition, and you can get the exact solution. And the Urals method, also Zona 6, place the force point at quarter core and the control point at 85% core. And the force point at the quarter core also, by following the 2D steady thin airfoil theory, the control point at 85% core is based on the countless numerical experience for evaluation of many wing platforms. The JETIC analytically proved that the best control point on the infinite wing using Urals method is at 88% core. And however, for unsteady flow or highly swept wing, the center of pressure may not be at a color core. Okay, so this color core assumption may not be valid for highly swept wing or unsteady flows. However, because the unsteady flow in unsteady flow, the unsteady pressure distribution at high frequency could be highly oscillatory. So in order to capture this highly oscillatory distribution, we usually need a large number of boxes than the steady aerodynamics model. And a large number of boxes can reduce this discrepancy from the color core to the actual center of pressure of highly swept wing or in unsteady aerodynamic flow. Then we compare the steady and unsteady panel method, and so we can show that the Stokes theorem also can be applied to the integral solution of the unsteady small disturbance potential equation, and then we also can convert the velocity potential to acceleration potential, because the acceleration potential satisfy the unsteady boundary condition on the wake. So we don't have to model the wake. Okay, and so we only solve the acceleration potential on the surface itself. And for the steady panel method, the vortex lattice method use the constant doublet, and the Urals method use the linear doublet. Pan-Air use the quadratic doublet. So the Pan-Air is has the highest order formulation. Okay, and the vortex lattice method is the lowest order method. And for the unsteady panel method, and the unsteady extension of Pan-Air is called A502. It has the highest panel formulation. The double lattice method is the lowest one, and Zona 6 also use the linear doublet assumption. Okay, so if we look at a 70-degree delta wing, and if we cut the wing into 10 by 10 boxes model, and because the DLM requires the aspect ratio of the box to be less than 3, and Zona 6 is free from this aspect ratio restriction, because Zona 6 is a higher order panel model, panel method. Okay, so if you plot the CP along the station 8, and if you plot the CP from the Zona 6 and the double lattice, both CP are pretty smooth. But if you plot CP along the wing T, the double lattice method becomes zigzag, and whereas Zona 6 CP still is smooth. If you further increase the core-wise cost from 10 cars to 40 cars, you're going to make the WS solution become worse. Right? So if you look at stage 8 and the double lattice solution shown by the solid line start have some zigzag, and zone 6 solution shown by the dot is smooth, and along Winty and the double lattice solution become highly zigzag, and meanwhile the zone 6 solution still is very smooth. And the unsteady pressure at high frequency has highly oscillatory behavior. A linear doublet distribution has better fit than that of a constant doublet distribution. So if you use a constant doublet, try to capture this oscillatory CP, you need a lot of boxes. But if you use a linear doublet to try to capture this highly oscillatory CP distribution, you need less number of boxes. So zone 6 requires less boxes than the DLM to achieve a converged solution. And this is a convergence study on the BAH wing at Mach 0.8. If we plot, there's 2 modes. The first mode is plunging mode. The second mode is pitching mode. So we have the real part of Q11, imaginary part of Q11, the real part of Q22, imaginary part of Q22, and we set up the panel model. First, we fix the span-wise strips to be 100. So we have a 100 span-wise strip. Then we increase the core-wise box from 30 to 60 to 120. Then we look at the real part of Q11 and imagine Q11 and Q22 versus the reduced frequency from 0 to 5. Okay, if you look at the zone 6 solution from the 30 core-wise boxes to 60 core-wise boxes to 120 boxes, both the real part of Q11 and the Q22, and it is shown by those 3 lines. Those 3 lines hardly move. Okay, while we increase the core-wise boxes. But if you look at the double-S solution, and this is the 30 core-wise box, this is 60 core-wise box, this is 120 box. So the DLM solution, when you increase the core-wise boxes, and it gradually approaching the solution of zone 6, while zone 6 solution hardly change when we increase the core-wise box. So this shows that if you use the higher order panel method like zone 6, you need less number of boxes to achieve a converged solution at a high frequency. So the conclusion, the DLM has been accepted by the flutter engineers as a standard unsteady aerodynamic method for many years, but it does not imply that DLM always provide accurate solution. The user must be aware of the modeling restrictions and the high frequency issues. Zone 6 is an extension of the Woodward's method for unsteady aerodynamics, and Woodward's method is a standard steady aerodynamic method used by Lowe's engineers. At 0 frequency, zone 6 and Woodward's solutions are identical. Compared to DLM, zone 6 has less modeling restrictions and require less boxes to achieve a converged solution.
Zone 7 is a supersonic unsteady aerodynamic method. It is the counterpart of the zone 6 in supersonic flow, and it can generate steady and unsteady supersonic aerodynamics for wing body aircraft configuration with the external stall, and also it can model any combination of planar, non-planar lifting surfaces with the arbitrary body, including fuselage plus stalls plus tip missiles, and for the lifting surface, the panel formulation of zone 7 is identical to that of the Zona 51. Zona 51 is in MSc NetTrend, and now is the industrial standard method for supersonic flutter analysis. And we have validated Zona 7 with internal measured flutter boundary and also the stability derivatives. In ZSAP, is for sonic acceleration potential panel method. So if at sonic speed, because Mach number is 1, so this term drop off. So we solve this partial differential equation, and you have the kernel function of the integral equation of sonic flow is different from the Zona 6 and the Zona 7. Like the Zona 6 and Zona 7, you also can model any combination of planar and non-planar lifting surface with arbitrary body. And and why we need a ZSAP for sonic flow? Because if you look at the government equation of Zona 6 and Zona 7, and when Mach number equal to 1, and because beta equal to square root of 1 minus m square, and when Mach number approach 1, beta becomes very small, so this term becomes very large. So you may have a convergence problem if the panel model is not very refined. Therefore, we developed this ZSAP. And showing here is a sub Kernel wing configuration. And if we calculate the Q12, which is lift due to Kernel pitch mode, oscillate at different reduced frequencies. And if we use ZSAP, and the solution is shown by the black dots. Now, if we run Zona 7 at Mach number 1.01 and Zona 6 at Mach 0.99, and if the panel model consists of 10 by 10 boxes for the Kernel and 20 by 20 for the wing, and you can see the Zona 6 and Zona 7 solution become zigzag. That means they are not convergent solutions. If we increase the panel model from 10 coax cut on the Kernel to 50, and increase the coax cut on the wing from 20 to 90, and this time if we run Zona 6 and Zona 7, they have a very smooth solution and agree with the ZSAP solution at the Mach 1. So, and also if you compare the ZSAP solution with using the coarse panel model with the solution using the refined panel model, you will find the ZSAP solution almost the same. And this implies that the ZSAP solution already converge using the coarse panel model. So this is to say that if the Mach number close to 1, and Zona 6 and Zona 7 may have convergence problem unless you use very refined panel model. However, if you use ZSAP, even you use a coarse panel model, you can get a convergent solution. And also we have validated ZSAP flutter solution on the AGA 445.66 wing. And Zona 7U is for hypersonic Uncity aerodynamics, and if you use Zona 6, Zona 7, and ZSAP, you do not need to model the airfoil section because the airfoil thickness effect cannot contribute to the Uncity linear potential equation. However, if for the hypersonic unsteady aerodynamics, you have to include airfoil thickness. The Zonal 7U incorporate the so-called rotationality correction to the Zonal 7, and then we have Zonal 7U. So to use the Zonal 7U, you must include airfoil thickness, and we have validate the Zonal 7U with a wind tunnel measure from the boundary, and also the CL alpha at Mach number 4 and at the various reduced frequencies. And in this example, this is a 15-degree wedge of the airfoil, and the wing is a rectangular wing because wingspan is large, and so the tip effect will not influence the CP at the center of the wing. So the CP at the center of the wing become a purely two-dimensional flow. And so in this case, we have a 2D Euler unsteady solution for this configuration. And if we compare the real part of CL alpha and imaginary part of CL alpha at reduced frequency from 0 to 5, and so the Zonal 7U is shown by the block box, and the exact Euler solution is shown by the triangles. You can see they have a very good agreement. However, if you use Zonal 7, which cannot include the airfoil thickness effect, you have a solution right here. And if you use piston theory, and also you have a solution there. So this this example shows the Zonal 7U can capture the hypersonic effects. And the last method is called Z-Trin. And if we go back, because Z-Trin solves the linearized unsteady transonic small disturbance equation, which is this equation. It consists of three parts. First one is the surface integral. The second one is the volume integral. The third one is the surface integral integrate around the shock surface. Okay, so and okay, so we have a three integrals solutions, and to give you a velocity potential equation at a control point x0, y0, z0. However, those two integral, the volume integral and the shock integral, going through the integration by parts, we can combine those two integral into one volume integral. Well, sigma v, how do we evaluate sigma v? Walls suggests that the volume source term sigma v can be evaluated using the Merman finite difference operator, showing in this equation, where mu is 0 if the local Mach number is subsonic, and mu equals 1 if the local Mach number is a supersonic. Because in transonic flow, the flow is mixed by subsonic and supersonic flow, and in front of the shock, the flow is supersonic, and behind the shock, the flow is subsonic. So it's a mixed flow, and so this Merman finite difference operator is a conservative scheme, and guarantees the correct mathematical shock jump. It automatically switches from the central differencing in the subsonic flow to the backward differencing in the supersonic flow. So introduce the directional bias to the integral equation of the time linearized small disturbance equation for the mixed flow problem. And then based on this Merman finite difference operator, we can rewrite this operator in the matrix in a matrix form. So sigma v equal to T times phi. Phi is the unsteady velocity potential, and the time linearized equations involve the steady velocity called phi naught x. So we define this as a steady background flow, and that can be imported from the high fidelity CFD solver. And so in Z-Trin method, we do not solve the nonlinear steady TSD equation. The correct steady transonic shock location provided by the high fidelity CFD solution ensures that the correct unsteady shock location. So in order to solve this volume integral, we have to put the so-called volume block on the upper and lower of the lifting surfaces, also the volume block around the bodies, and then we divide the volume block into many small volume cells. And so for the point on the surface, and the normal velocity can be related to the AIC matrix times the delta Cp and the unknown source term. This AIC is identical to that generated by the zonal 6 method. And also we have another matrix, which is B. B is the inference from the volume cell to the control point on the surface times the sigma v. And for the point in the volume cell, the velocity potential can be calculated based on a matrix C. Matrix C is the inference from the surface delta Cp and the source term to the centroid of the volume cell, plus a matrix D times sigma v, and D is the inference coefficient from volume cell to volume cell, and sigma v can be replaced by T times phi, and then we have this equation. So we combine the phi together, and we can relate phi to the unknown surface delta Cp and the source singularity by through this two matrices, where E inverse the matrix E is shown here. For points on the surface, the normal velocity becomes the HJ times delta Cp times the unknown source term, and also it is this matrix times the unknown delta Cp and the source term on the surface panel model. So we combine those two matrices, we call AJJ bar. So AJJ bar is shown here, and so the AJJ, if we invert the AJJ bar and times the FJK times HK is the 60 degree of freedom of the mode shape in KSAT, and pre-multiplied by the integration matrix SKJ, we have AIC matrix. And then this AIC matrix generated by the Z-Trin method has the same size of that generated by zonal 6, zonal 7, and Z-set. So because AIC matrix generated by the Z-Trin method has the same form as that by other methods, it can be directly plugged into the downstream aeroelastic modules for transonic flutter AIC Trin and the dynamic load analysis. And however, if you look at the size of E, the size of E is the number of volume cells. The matrix E is a complex and fully populated matrix whose size is the number of volume cells. To model a single lifting surface, it may require more than 3,000 volume cells. This number increases rapidly for complex configuration. So solve such a large, complex, and fully populated matrix is impractical. So we use a block tridiagonal approximation to decompose the matrix E. So we can split the matrix E into two matrices. One is called E sub B, one is called E sub epsilon. E sub B is a block tridiagonal matrix whose triangular blocks contains the inference coefficients from self block and adjacent block. So, and E sub epsilon contains 0 in the tridiagonal blocks, and the inference coefficient from the non-adjacent blocks to the off tridiagonal blocks. And because the integral equations contains a function of 1 over r. R is kind of a distance. So this function decays rapidly when the point at a control point is away from a volume cell. So all elements in the E sub epsilon are small. So we can approximate the inverse of E by this equation, because E sub B is a block tridiagonal matrix. The inverse of E sub B can be computed efficiently using the Thomas algorithm. And later on, we're going to show when you set up the Z-Trin volume block model, you have to help the Z-Trin to establish the block tridiagonal form. And for the complex configuration, and the Z-Trin use so-called overset field panel scheme. And the overset field panel scheme minimizes the cell generation effort for complex configuration. And so in this overset field panel method, the volume cells surrounding each individual lifting surface body are generated independently as defined as one group of cells. Cells of different groups may intersect with each other, and this gives us an overset field panel method. Therefore, for a wing with the underwing missile, we just generate a volume block on the upper and lower surface of the wing, and we generate a volume block around the missile body, and we generate the volume block on the upper and lower surface of each missile fin. The integral equation of the overset field panels are formulated based on the following scheme. Volume cells in different groups do not influence each other. Volume cells in the same group influence only their associated surface box, and surface box influence all volume cells. And unlike the overset CFD methodology that requires the interpolation of a flow solution among the overlapping region between different groups of CFD mesh, the field panel method automatically transmits the interference between groups to the integral equation. So interpolation of flow solution is not required, and no need to compute the topology of the intersection among cells. And in the overset CFD scheme, they use so-called the camera scheme. They have to perform so-called hole counting, and then they have to compute interpolated flow in the overlapping mesh region. But Z-Trin is an integral equation, so we do not need to compute the topology of the intersection region among cells. And because Z-Trin solves the transonic small disturbance equation, then it is well known that transonic small disturbance theory may not provide accurate solutions for strong transonic shock cases because it cannot correctly model the entropy gradient from the strong shock nor convect the vorticity. However, this is not to say that the transonic small disturbance theory is not suitable for the prediction of unsteady flows due to small error elastic deformation. If the total unsteady flow is decomposed into a steady background flow and unsteady small disturbance. So this is exactly what Z-Trin is doing. It imports the high fidelity CFD solution as the steady background flow and solve for the small disturbance solution of the unsteady velocity. So because the steady background flow in the time linearized TST equation is externally provided by a high fidelity CFD steady flow solution, accurate unsteady flow prediction can be ensured. This is also evident by examining the Merman scheme, where the switching scheme from the central differencing to the backward differencing is based on the local Mach number of the steady background flow. So if the local Mach number are computed by the high fidelity CFD solver, so the switching from the central differencing to the backward differencing in Z-Trin is based on the local Mach number. So thus the unsteady shock location is dominated by the steady shock location in the small amplitude sense, implying that the accurate steady shock structure can ensure the accuracy of the unsteady shock structure. So we have validated Z-Trin with the many wind tunnel flutter boundary, and also wind tunnel measured the unsteady pressure. So as we mentioned, Z-Trin give you a AIC that has the same form of AIC computed by zone 6, zone 7, and ZSAT. So once the AIC is generated by Z-Trin, it can plug into the downstream error elastic module like Flutter, AIC, and Trin, and so on. We will show one of the case to validate the Z-Trin. The case is called Trin engine transport model. This model was tested in TDT, and this wind tunnel model was conducted by the Boeing engineers in the transonic dynamic tunnel, and based on the measured flutter boundary of the Trin engine transport model, and between Mach 0.77 and Mach 0.82, they measured two flutter modes. The first one is called wind nacelle mode, which is which flutters at about 17 Hertz. The second one is called wind tip mode. It flutters at 22 Hertz. And in the wind tunnel, at a given Mach number, they increase the dynamic pressure gradually from low to high, and between Mach 0.77 and Mach 0.82. And when they encounter the so-called wind nacelle mode, and the test engineer had the courage to keep on increasing the dynamic pressure until they hit the wind tip mode. So this shows that between Mach 0.77 and Mach 0.82, the wind nacelle mode is a low has a low unstable damping, therefore is a hung mode. So once flutter occurs, it turns into a limit cycle oscillation with a small amplitude. So the test engineer had the courage, still increasing the dynamic pressure until they hit the wind tip mode, and once they hit the wind tip mode, this winding mode is a violent flutter, so they have to stop the test. However, above Mach point 82, when they hit the wind nacelle mode, the LCO amplitude become large. So they are afraid that the wind tunnel model encounter structural failure. So they stop increasing the dynamic pressure. So they did not they could not measure the flutter boundary of the winding mode at Mach number above Mach 0.82. And the structural model has 16 natural modes, and we set up the service panel model of this twin engine transport flutter model, and we interpolate the mode shape from the structural grid to the aerodynamic service panel, and this shows the interpolate mode or spline mode on the aerodynamic model for the first 4 natural modes. And the Boeing also give us a CFD solution. The CFD match is a structural match, and they use CFL 3D and compute the entire flow field. And the Z-Trans service model contains 380 boxes for the wing, 30 boxes for the pylon, and 3 or 4 boxes for the fuselage, and 96 boxes for the engine nacelle. And the CFD mesh contains of 29 blocks and 3 million surface grid. So on top of the service panel model, we generate the volume cell, and the volume cell model for the twin engine transport model contains 24 by 20 by 40 volume cell for the wing, and that much volume cell for the pylon, that much volume cells for fuselage, and that much volume cell for the engine nacelle. So volume cell on different components intersect with others. The inference between volume cell is properly computed by the overset field panel scheme. The steady mean flow solution is automatically interpolated from the CFL 3D steady never solid. So we look at the steady CP at a different Mach number and angle tag equals negative 2 degrees. So you can see as the Mach number increase, the transonic shock move toward the wing trading edge, and then we calculate the flutter boundary at Mach 0.79 and Mach 0.883, and the solid symbol are the wing nacelle flutter boundary and wing tip flutter mode flutter boundary computed by the Z-Trans. The hollow, the open symbols are the 6 solutions. So first, let's look at the Mach 0.79, and if we assume the viscous damping of the structure to be 1.5%, then when you cross this 1.5% damping line, the Z-Trans predict the flutter boundary of the wing nacelle mode is at a dynamic pressure around here, and whose corresponding flutter frequency is 17 Hz. So the wind tunnel test flutter boundary of the wing nacelle mode is right here. So we slightly under predict the flutter boundary by Z-Trans. However, the flutter frequency agrees very well with the wind tunnel measured flutter frequency, and also the Z-Trans solution shows that the engine the wing nacelle mode flutter mechanism is a hum mode. So this also agree with the wind tunnel observation. Okay, but for the wing tip mode, it is once the damping line cross the 0 and 1.5% damping line, it's become a violent flutter. This also agree with the wind tunnel observation. And Z-Trin predict the flutter dynamic pressure is right here, so it is slightly over estimate when compared to the wind tunnel test data. But the Z-Trin predict this flutter frequency of the wind tip mode is 22 Hz. Also agree with the wind tunnel measured data. At Mach 0.83, and you can see for the wind nacelle mode, and even it is still a hum mode, but the unstable damping become much larger than the low at a low Mach number. Therefore, once it in the post-flutter dynamic pressure, the LCO amplitude become large. So this also agree with the wind tunnel observation, and the flutter dynamic pressure computed by Z-Trin for the wind nacelle mode just slightly larger than the wind tunnel measured data. And this is the wind tip mode, and it agrees very well with the wind tunnel measured data. On the other hand, if we use zone 6 to compute the flutter solution for the wind nacelle mode, is shown by the open circles. It does not crosses the 1.5% damping line. So zone 6 predict that there's no flutter for the wind nacelle mode. Also at Mach 0.83, just barely cross the 1.5% damping line, and for the wind tip mode, it largely over predict the flutter dynamic pressure. So this shows that for the transonic flutter prediction, you have to use Z-Trin. And we also compare the Uncity CP at two reduced frequency at Mach 0.79 and Mach 0.83. We compare the Z-Trin solution with the zone 6 and with the Trin-Air. Trin-Air is a transonic Uncity aerodynamic method developed by Boeing. Okay, and Z-Trin solves the full potential equation, and with the boundary layer coupling option. So at span station close to the wing tip, and the Z-Trin predict shock, Onslay shock, is ahead of the of that predicted by Trin-Air, and because the Z-Trin steady background flow is calculated by the Navier-Stokes solver, therefore it has a viscous effect, and whenever you have a viscous effect, the transonic shock is ahead of the inverse solution. So this one shows that the Z-Trin unsteady CP is correctly captured by Z-Trin. And but the point is that if you look at zone 6 solution, which is shown by the dashed line, it cannot capture this transonic shock effect. Therefore, the zone 6 solution is very inaccurate in transonic flow. And finally, we compare the flutter boundary of the wing nacelle mode and wing tip mode, and at various Mach numbers, and we assume we use different damping level from 0% to 1.5% to 2.5%, and the open diamonds are the wind tunnel measured flutter boundary of the wing nacelle mode, and you can see the wind tunnel data shows that even you repeat the wind tunnel test at the same Mach number, but sometimes you get a different measured flutter dynamic pressure. That means the wind nacelle mode, because it's a Helm mode, so it's very, very sensitive to uncertainties in the structure or in the flow condition. And then this one shown if we assume the structural damping to be 2.5%, and we have a good agreement with the wind tunnel measured data of the wind nacelle mode. And for the wind T mode, we also have a good agreement with the wind tunnel measured flutter boundary. Meanwhile, Boeing used CF3D to conduct a time domain flutter analysis. And they also have a good agreement of the flutter boundary of the wind nacelle mode. But they overpredict the flutter boundary of the wind tip mode. And beyond Mach 0.83, the CFL3D encounter so-called gray crossover problem, and therefore they cannot get the flutter solution above Mach number 0.83, and the CFL3D computation at each Mach number and takes about thousands CPU hours, and ZTrain for ZTrain to compute the flutter boundary only take about less than a day to have the flutter boundary at all the Mach number range. Also, we can show that ZTrain can predict the control surface bus. Control surface bus is a self-excited dynamic area instability problem, which is normally associated with the in-phase interaction between the forward and backward motion of the shock on the surface of the wing and the control surface oscillation in transonic or at a low supersonic Mach number. And control surface bus is a special case of flutter, and the control surface bus requires only one degree of freedom motion, namely the control surface rotation mode. Flutter requires the coupling between at least two modes. To distinguish the control surface bus from buffet is rather easy. From buffet is rather easy. Buffet occurs only at the high angles of attack, which results massive flow separation from the forward section of the aircraft. This separate flow impinges on the twin tail section, acting like a random forcing function that could lead to a large vibration on the tail, thus induce a fatigue problem. Control surface bus could occur even at a zero angle attack. And because the control surface bus involves the transonic shock, so you have to use a transonic method to predict bus. And the Lambro categorized the control surface bus into three types. The first one is called type A. Type A bus occurs normally in transonic flow for thin wing at a non-zero angle attack, or for thick wing even at a zero angle attack. And the shock of the type A bus never cross the hinge line of the control surface, and the type A bus is induced by the boundary layer separation induced by the shock, and this boundary layer separation has its own characteristic periodicity, which could couple with the control surface rotation mode, leading to bus. And the resulting oscillation of the control surface bus, control surface rotation, is usually harmonic motion. And the type B bus is a shock already crossed the hinge line located on the control surface. And in front of shock, we have local supersonic flow, extend rearward to the control surface and terminate by a shock wave. This happens normally at a high transonic Mach number on the thin wing, even at a zero angle attack. The bus instability is induced by the coupling between the shock and the control surface oscillation, in which the shock wave could cross the hinge line of the control surface. The response of the type B bus is normally periodic. Type C bus occur at a low supersonic Mach number. At a low supersonic Mach number, the shock wave extends to the trailing edge of the wing. The resulting oscillation is harmonic. And why type B type B bus and type C bus is harmonic response, and type B is a periodic response. If we look at the type A bus, because the shock never cross the hinge line of the control surface, so if you integrate the CP on the control surface to obtain the hinge moment, and you'll find out this area underneath the CP, and is proportional to the control surface deflection. But when control surface deflection becomes large, and it creates a flow separation. So in this at high control surface deflection angle, the flow becomes stable. Therefore, the control surface bus usually leads to limit cycle oscillation. But within the amplitude of the limit cycle oscillation, the hinge moment of the control surface is proportional to the deflection angle. Therefore, the equation of motion is the ordinary equation of motion with a constant coefficient, because the hinge moment slope is constant, and the solution is a sine is in terms of the sine function. Therefore, the response is harmonic. Same thing for the type C bus. for the type B bus, if you look at the hinge moment, once the shock crosses the hinge line, all of a sudden you have a sudden increase of the hinge moment. Therefore, the hinge moment slope is not constant. Therefore, the equation of motion is a linear equation with a varying coefficient, and the solution of this type of equation is periodic. And so for type A bus, because type A bus involves shock-induced boundaries, the boundary layer separation, the prediction of type A bus onset flow condition requires a viscous Uncity aerodynamic method, such as the Uncity Navier solver. For type B and type C bus, because it only involves the motion of the Uncity transonic shock, the inverse Uncity aerodynamic method, like an Euler or transonic small disturbance method, can predict type B bus, and so in the zonal Euler Uncity solver or the Z-Trin method in ZAERO can predict type B bus. For type C bus, because it does not involve transonic shock and only occurs in the low supersonic Mach number, the linear Uncity supersonic potential method, like zona 51 in Lagrange or zona 7 in ZAERO, can predict the onset of type C bus. Bus usually lead to limit cycle oscillation, sometimes up to plus minus 10 degrees, because when the control surface deflection angle is large, the flow separates, and in that separate flow, the aeroelastic system of the control surface mode become stable. So this creates a bonding mechanism, and so the control surface oscillate within this region, and leads to limit cycle oscillation. Now we want to show that the Z-Trin can predict type B and type C, type B bus, and Zonal 7 can predict type C bus. So this is a wing aileron model, and the aileron mode is around 5.6 hertz, and and we use Zonal 6 and Zonal 7 to generate a panel model, and then we put a volume cell on top and above and below the lifting surface, and we use the Zonal Onslay solver to calculate the steady background flow and import into the Z-Trin method at Mach 0.95, and so you can see at Mach 0.95 the transonic shock already crossed the hinge line, so at Mach 0.95, if it bus, it is the type B bus. And if we use 10 modes to perform flutter analysis, and this is the so-called the VG diagram and VF diagram predict by Z-Trin. So Z-Trin predict that there is a damping crossing at zero damping line, and the flutter speed is not much, and the flutter frequency is 5.81 hertz. If you use Zonal 6 at Mach 0.95, it predicts the flutter speed is much higher than the one predicted by Z-Trin. If we use Zonal 7 at Mach 1.1, we also predict the flutter speed is around this number, and the flutter frequency is around 5.7 hertz. So you can see the Z-Trin at Mach 0.95 and Zonal 7 at Mach 1.1, the flutter frequency is very close. However, if you use Zonal 6, the flutter frequency is 6.33 hertz. Apparently, the flutter mechanism captured by Zonal 6 is not a control surface bus. So if we look at the flutter mode computed by Z-Trin at Mach 0.95, you can see it's almost a purely aileron rotational mode. If you look at the Zonal 6 at Mach 0.95, apparently it is a bending torsion coupling mode. And if you look at the flutter mode computed by Zonal 7, also is an aileron rotational mode. And if we only use one mode, which is aileron rotational mode, and the Z-Trin also can capture flutter instability. The frequency is also at 5.8. If you use Zonal 7, even with one mode, it also capture instability, also at the frequency at 5.75. If you use Zonal 6, it cannot capture any flutter instability, because Zonal 6 cannot capture the bus instability. So if you look at the Z-Trin solution using one mode, still is a flat-plane aileron rotational mode, and Zonal 7 also is a aileron rotational mode, and Zonal 6 cannot capture any flutter instability. So if we compare the flutter solution, and if we use Z-Trin with 10 modes with one mode, and the flutter speed has a small difference, but the flutter frequency change very little. And for Zonal 7, if we use 10 mode and one mode, the flutter speed is change very little, and the frequency almost the same.
The Z-Tau module. Z-Tau module performs AIC correction method, and it generates a corrected AIC matrix to match the given set of force and moment or unsteady pressures. The AIC correction module computes the AIC weighting matrix using a zonal transonic AIC weighting we call ZAERO method that uses a successive kernel expansion procedure. The AIC correction method was widely used by the aerospace industry before the computational tools that can capture the transonic shock effect was developed. And even today, some aerospace companies still use the AIC correction method. The AIC correction method does not have a solid theoretical foundation. Therefore, sometimes it works, sometimes it doesn't. So it is an ad hoc method. The ZAERO method in ZAERO is an improved AIC correction method over the previous correction method, such as the force moment correction method by Giesing and the downwash weighting matrix method by Pitt and Goodman. With the in-phase pressure obtained by the wind tunnel measurement or computed by CFD, ZAERO can give you accurate out-of-phase pressure and higher frequency pressures, resulting in well-correlated aeroelastic solutions, whereas the previous method sometimes give you the wrong out-of-phase pressure in terms of shock jump behavior. And 4 methods are incorporated in ZAERO. The first one is a steady downwash weighting matrix method. The second one is unsteady downwash weighting matrix method. The third one is a steady force correction method. The last one is an unsteady force correction method. And what's wrong with the previous correction method? The force moment AIC correction method developed by Giesing and Jadek is shown here. Well, the force given is the given component loads, like the wind bending moment and hinge moment of the control surface, and that's the constraint function. With this constraint function and the AIC correction method computes a weighting matrix. So the A is an uncorrected AIC matrix. W bar is a downwash vector, which is an unsteady boundary condition, where H is the mode. And so AIC times W bar give you unsteady pressure, and the pre-multiplied by L is a load integration matrix. So that give you a component loads. And without the CF, the computed component loads may not match with the given component loads. So using a Lagrange multiplier method, and we can which trace this given component loads as a constraint function, we can calculate the matrix CF. So the CF times A is called corrected AIC. Once you have a correct AIC, and correct AIC times that W bar pre-multiplied by L will match with the given component loads. And once you have this correct AIC, then you apply the correct AIC in non-zero frequency and for all other modes. And the downwash weighting matrix developed by Pitt and Goodman, and is to calculate a weighting matrix called CD. So the CP given is a given pressure distribution as a constraint function, and then we want to calculate CD so that the AIC times CD times the downwash vector will match with the given CP. So A times CD is called the corrected AIC. And the Dongano method for unsteady pressure is calculated based on this equation, where R which is a function of a reduced frequency, and psi x is the velocity potential gradient of the unsteady flow, and psi x now is the steady flow. And so R times a given Cp at 0 frequency plus Ik times this integral. This integral is the integration of R times Cp given at 0 frequency along the clockwise direction. So we want to show the shortcoming of the previous correction methods. Those methods generally lack a rational procedure to obtain the auto phase and higher frequency pressure. And some provide good in-phase pressure because the in-phase pressure can be derived from the given steady pressure, but the out-of-phase pressure showed the wrong trend. And this is Dongano's method. This example case is a twin engine transport flux model at this Mach number, at this reduced frequency, and the steady pressure was given by Trin air. Trin air is the unsteady aerodynamic code developed by Boeing, which is shown by the solid line at two span station. If you look at this span station, and the solid line for the rear part of the unsteady Cp, the Dongano method match well with the Trin air solution. But if you look at the imaginary part, the shock jump behavior of the Dongano's method has an opposite sign from the Trin air solution. And this is this one shows the shortcoming of a downwash weighting method on the land wing at this Mach number, at this reduced frequency. The steady pressure is given by CFL 3D. So if you look at the rear part, again, the DWM match well with the test data. But if you look at the imaginary part and the shock jump behavior of the downwash weighting measurement method, it has an opposite sign from the internal measured imaginary CP. So what's wrong with this correction method? If we look at the Dongano's method, because the unsteady pressure formula can be expressed by this equation, where phi is a function of reduced frequency, and if we assume the reduced frequency to be small, and the phi x, which is a function of Ik, can be approximated by a phi xr plus Ik times phi x imaginary. So if we plug this equation back to this Cp pressure formula, and we can obtain this equation. In Dongano's method, the out-of-phase term phi xi is missing. Thereby, the imaginary part of Cp sometimes does not correlate with the internal data. For the downwash weighting method for small frequency, and because Cp equals the AIC times the weighting matrix times the boundary condition, and if reduced frequency is small, we can approximate the AIC matrix to be a AR, which is the real part of the AIC, plus Ik times the imaginary part of the AIC, and then that gives us this equation. And because the AR times CD, we impose the given CP as a constraint function to calculate CD. So AR star, which is corrected AIC, times the HX. If we assume the mode is a pitch mode, then the HX is like an angle tag. So if the CP is a dCP by d alpha, and then so this is the imposed condition. Therefore, the in-phase pressure is the given steady pressure. That is, the correct AIC contains the correct in-phase shock jump condition. However, the term AI star, which is AI times the weighting matrix, is all of phase pressure, is arbitrary. Thus, does not result in correct all of phase shock jump behavior. The above discussion suggests that all of phase pressure, the Vxi and AI star, cannot be obtained from the given in-phase pressure. They must be obtained from the rational formulation, which is based on the Uncity equation. And Z tau uses the successive kernel expansion procedure, consists of the following step. First, we obtain the corrected AIC at 0 reduced frequency using the downward weighting method. Then we inject the correct AIC at 0 frequency back to the linear potential equation to recover the all-of phase pressure. So this equations show how the successive kernel function expansion to recover the all-of phase pressure. And we have validated the Z tau module on several configurations and for the Uncity pressure, and also we validate the flutter boundary on the AGAP 445.6 wing and the Papa wing. And the CP given is computed by CFL 3D Navier solver, and we calculate the CP at two different angle set or tag. Then we use finite difference to calculate the dCP by d alpha. So the first test case is F5 wing pitch mode, about 50% root chord at Mach number 0.9 and the reduced frequency 0.275. And the first one, we want to look at the steady CP computed by CFL 3D Navier solver. You can see the CFL 3D steady Navier solver did a very good job. And then we use the finite difference to compute the dCP by d alpha. And this is dCP by d alpha for the steady flow. And we inject this dCP by d alpha into the Z tau to calculate Uncity pressure. So the Uncity pressure is the F5 wing pitching about 50% root chord at Mach 0.9 and the reduced frequency 0.275. And if you look at the rear part, the solid dots are the wind tunnel data at the various span stations. The solid lines are the Z tau solution, and for both the real part and imaginary part, and you can see the Z tau solution correlates well with the wind tunnel test data. But if you use the DWM, which is shown by the dashed lines, in the real part, it correlates good with the test data, of course, because of as I said, because the real part is almost equal to the imposed dCP by d alpha. But in the imaginary part, you can see the Z tau module, the DWM cannot capture the Uncity shock jump. The next case is F5 wing pitching about 50% root chord at Mach 0.945 and this reduced frequency. Again, we compare the CFL 3D Navier solver at a 0 angle tag, and you can show CFL 3D compared with the internal data, and the comparison is very good. Again, we use CFL3D to compute the CP at the angle tag 0.5 degrees, and then we use the finite difference to calculate the dCp by d alpha. Then again, we inject the dCp by d alpha into z tau, and then we correlate the z tau solutions, which is shown by the solid lines, and compared to the internal data, which is shown by the black dots. And both the real part and imaginary part at different span stations, the z tau correlate well with the internal data. Again, if you compare the DWM solutions, which is shown by the dashed lines, in the real part, the DWM correlate very well with the internal data. But if you look at the imaginary part, and especially across the shock, the shock jump behavior is opposite from the internal data. The next case is the Langwin in pitch mode, about 62% record at Mach number 0.822 and the reduced frequency 0.105. And again, we use the CFL3D Nemesis solution to calculate the steady CP at this Mach number and at this angle tag compared to the wind tunnel. And again, CFL3D Nemesis solver did a very good job. Then we use the finite difference method to calculate the dCp by d alpha, and which the dCp by d alpha shows that they have spikes, and those spikes actually correlates with the it's caused by the steady shock, because in the steady flow, once the shock occurs, the CP across the shock has a rapid change in slope. So if you take the derivative of the steady CP with respect to the angle tag, and you will have a spike. And then we inject this dCp by d alpha into z tau, and also the DWM method, and at different span stations. And again, the z tau solution is shown by the solid lines, and the solid dots are the wind tunnel data. The real part, both z tau and DWM solution correlate with the wind tunnel data very well. And but if you look at imaginary part, the z tau solution give you correct shock jump. But if you look at the DWM solution, it gives you the wrong shock jump. The next case is called Langwin in first bending mode at this Mach number and this reduced frequency. And again, CFL3D can give you very accurate steady CP. Then we use the finite difference and to calculate the dCp by d alpha. And then we compare the Uncity CP at this Mach number, this reduced frequency in magnitude and the phase angle. And so the solid lines are the z tau solution. The dashed lines are the zona 6 solutions. Compared to the wind tunnel result, you can see the z tau can give you a correct shock jump behavior, whereas the zona 6 cannot capture the Uncity shock, thereby give you poor correlation. Then we compare the flutter boundary of the Papa wing with the wind tunnel measured flutter boundary, and this is the flutter dynamic pressure at various Mach number and the flutter frequency at various Mach numbers. If you use DWM, which that under-predict the flutter dynamic pressure, if you use zona 6, which is the linear potential method, it over predicts the flutter dynamic pressure. But if you use Z tau give you accurate flutter dynamic pressure, and so Z tau method is a better method than the DWM method. Now you may ask, if we have Z-Trin which can capture transonic shock effect, why we need a Z tau? And this because of accurate hinge moment of a control surface is difficult to predict using computational method, even if you use number solver. So showing here is the Uncity CP distribution on the BACT wing due to trailing edge flap oscillation. The solid diamonds are the TDT data, the wind tunnel measured data, and the right lines are the CFL3D Uncity solutions. And the first spike located at 40% core is caused by the transonic shock, because at this Mach number, and the transonic shock occurs at 40%. So CFL3D Uncity solver capture the shock jump. And then the second spike is due to the is at 80%, which is a hinge line location, and it's due to flap oscillation. And then in general, you can see the CFL3D unsteady solution correlate not so bad with the wind tunnel data. But if you look carefully, especially on the trailing edge flap, at the trailing edge, the CFL3D unsteady solution over predict the magnitude of the CP. And because the hinge moment is integration of the CP on the flap with respect to the hinge moment. So at the trailing edge, it has the largest moment on. So this over prediction times the large moment on will show you that CFL3D Uncity solution over predict the hinge moment. The accurate hinge moment sometimes is critical for flutter prediction if the control surface rotational mode is involved in the flutter mechanism. One example is a T46A jet trainer, and this trainer encountered an unexpected flutter oscillation in flight test, and this flutter mechanism involved the interaction of the aileron rotational mode with the wing bending mode. Okay. T46A was designed by a company called Fairchild, and because of this flutter problem, the U.S. Air Force canceled this project, and the Fairchild went under. So this is a tragic example to show that a flutter problem could cause a company went bankrupt, and the flutter analysis before the flight test they used the linear theory, but they did not predict this instability. And then they compared the wind tunnel data. The hinge moment computed by the linear theory is over predicted. So they should reduce the hinge moment, and then use the reduced hinge moment to predict the flutter boundary. So the post-test flutter analysis showed that the flutter speed highly depends on the hinge moment, and when the hinge moment is reduced to 63%, aileron rotation and wing bending flutter mode is predicted. So it is shown by this VG diagram. When they apply a knockdown factor on the Uncity CP on the flap by 63%, this damping line crossed the zero damping line. Therefore, they predict the flutter instability at this speed, and this speed correlated with the flight test data. Therefore, it is highly recommended that a Z-trend be used to account for the transonic shock effect. Then, you should use Z tau to correct the Uncity CP due to control surface mode. And some other cases, you should apply Z tau, because almost all Uncity potential panel methods, including Zona 6, Zona 7, ZSAP, and Zona 7U, as well as double lattice method, implicitly assume that the wake shading from the trailing edge of the wing to be a flat sheet of surface and parallel to the x-axis. So the wake surface is prefixed by those methods. And therefore, the lateral and directional stability derivatives are not accurate. For example, at a side slip angle, the wake should be nearly parallel to the free stream direction along the side slip angle, not parallel to the x-axis. So this implies that the lateral stability derivatives like Cn beta and Cl beta computed by the Uncity potential panel method are not accurate. For example, if you have a wing modeled by a flat plate at a zero angle tack and at a side slip angle, and in the real flow, the wake should be nearly parallel to the side slip angle, but because of the fixed wake assumption, those methods cannot predict the correct rolling moment. Okay, so therefore, in this case, you have to use the Z tau method to correct AIC, thereby give you correct lateral and stability, lateral and the directional stability derivatives. Another example, for coplanar wing tail configuration at a negative angle tack. In the real flow, the wake from the wing passes through underneath the tail. Because the Uncity potential panel methods assume that the wake slightly passes above the tail, the unsteady aerodynamic loads on the tail in the coplanar configuration predicted by the Uncity potential panel method are not accurate due to the inaccurate downwash angle. Therefore, the aerodynamic stability derivatives such as CL delta and CM delta are not accurate for the coplanar wing tail configuration, like the canard fin configuration on missile. So in this case, you also need to apply Z tau method. And another case, because the lateral gas at a zero frequency is Cn beta, the generalized aerodynamic forces of the lateral gas force must be corrected by AIC correction method or by a RBQHH Voltaire car. We're going to talk about this car later. The final example is a TTL configuration. The TTL configuration is a flutter critical component. And the generalized aerodynamic forces of the rolling moment due to vertical tail rotation mode is a dominant term in the TTL flutter mechanism. And because the GAF at the K at a 0K is equivalent to the CL beta, it must be adjusted by the AIC correction method. This is because when the vertical tail undergoing a torsional mode, the horizontal tail will undergo a yawing motion, and during the yawing motion, the wake shading from the horizontal tail should oscillate according to the vertical tail torsional mode. But because of the fixed wake assumption, the rolling moment from the horizontal tail is not accurate. So you have to use Z-tau method to correct the AIC. Finally, we want to talk about the recommended applicable Mach number range of 5 Uncity aerodynamic method. If you have if the Mach number for the Mach number from 0 to 0.85 for thin wing and 0.75 for thick wing, and before this Mach number, transonic shock should not occur, so zona 6 is accurate. Of course, in those Mach number, you also can use Z-Tran because Z-Tran solution in this low Mach number range reduces back to that of zona 6 and zona 7. However, above this Mach number and to Mach number 0.98, you should use Z-Tran. Also, from Mach number 1.2 to Mach number 1.02 to Mach number 1.2 for thin wing, Mach number equals 1.5 for the thin wing. You also should apply the Z-Tran method. Above this Mach number, below Mach number, like Mach number equals 3, you can use zona 7. But in hypersonic flow, you have to use zona 7U. Before Mach 0.98 and 1.02, and because unsteady flow is highly oscillatory due to the term 1 over square root of 1 mass m squared, and in this Mach number range, you should use Z-tau. So if you want to perform aeroelastic analysis between this Mach number, you just set Mach number equal to 1 and you activate Z-set.
Section 4.2 Bulk data card input for generating the AIC matrix. And all the cards are related to the generation of AIC matrix. The only required card is called MK-LZ card. And in this card, you define the Mach number, reduce frequencies, and aerodynamic method for the Uncity aerodynamic data generation. And in this slide, we showed the bulk data cards and the processing procedure for generating the AIC matrix. So based on the aerodynamic model, the MK-LZ card and defines the Mach number and the list of reduced frequencies, and then it generates the AIC matrix. If you have a half-span model, and the MK-LZ card will internally generate a symmetric AIC and anti-symmetric AIC matrices. If you have a full-span model, it will generate an asymmetric AIC matrix. And MK-LZ card also refers to a Trin flood card. In the Trin flood card, you define the mean flow condition in terms of angle attack, side slip angle, and control surface deflection. If you want to run Z-Tran, you have to set up a volume cell model, and the Z-Tran method use a IMP CFD card to import the structured CFD solution, and also use the IMP CFD1 to import the unstructured CFD solution. And those two cards are referred to by the Trin flood card. So if you want to run Z-Tran, you have to refer to a Trin flood card. In the Trin flood card, and this card refer to the IMP CFD or IMP CFD1 card. And after you generate the AIC, at this step, you can apply the Z-tau to generate a corrected AIC. For the fourth correction method, the two cars called WT1 AJJ and WT1 FRC are used. For the downwash correction method, the car is called WT2 AJJ. And if you only want to correct the Uncity CP of selected mode, you use WT UCP. And meanwhile, if you want to generate the gas, you have to specify a gen gas car, and this gen gas car will generate the so-called QHG matrix. And once you have AIC matrix, and the MKLZ car can internally generate the unsteady CP. The unsteady CP is called AJH. Now, if for the symmetric AIC, then the AIC times the symmetric mode give you a symmetric unsteady pressure. For the anti-symmetric AIC, times the anti-symmetric mode shifts, it gives you anti-symmetric unsteady pressure. For the asymmetric model, you only have a asymmetric AIC, and then at this stage you can apply the CP factor. You can apply a factor to a set of panels and the CP on a set of panels, and then you can use the plus CP car to display the unsteady CP of a particular mode. And after we have unsteady CP, and then we multiply by a integration matrix called SKJ. It converted the CP to forces, and then pre-multiply by the mode shift matrix. That will give you symmetric generalized area and forces and anti-symmetric generalized area and forces called QHHS and QHA. And finally, if you have a rigid body mode, you can replace the rigid body sum matrix in the QHH matrix by the import aerodynamic stability derivatives. So this is a simple sample input of MKLZ car, and you give ID, Mach number, and then it refers to a Trin flat car. Then you say the mean flow condition is at angle tag 2 degrees. Then you list out the reduced frequencies. So the MKLZ car is a required car, and this car is not referred to by any other Voltaire car. All MKLZ cars are automatically processed to generate the unsteady aerodynamic data, regardless of whether or not they are used by the downstream disciplines. So in other words, in ZAERO, once ZAERO sees a MKLZ car, it will generate AIC matrix based on this MKLZ car. So save the AIC on the runtime database, and so if you want to generate the AIC matrix at many Mach number, you can put those MKLZ cars in input file and run ZAERO for over the weekend. Then you can get all the AIC matrices at different Mach numbers. The ID MK is the ID of MKLZ car. ID MK is referred to by many other cars. Okay, and then you specify a Mach number. And the further correction of AIC matrix can be done by the internal data or CFD results using the CP fact, RBQHH, WT1 AJJ, WT2 AJJ, WTQHH, or WT UCP. The entry method, you select a method for generating the AIC. And if you put 0 and the Mach number is subsonic,
you use 6. And if method equal to 0 and Mach number greater than 1, then you use 7. If method equals 0 and the Mach number is 1, then you activate the ZSAP method. If method equal to 2 or negative 2 and Mach number greater than 1, you activate the zona 7U method. If method equal to 3 or negative 3 and the Mach number not equal to 1, you activate the ZTran method. And if method equal to 4 and the Mach number greater than 1, you use the zona 7U, but with a steady background flow from CFD. And at the entry ID flat is referred to a trim flat card to define the mean flow condition. And so the Uncity aerodynamic data are computed by a perturbation about the mean flow condition. And if ID flat is 0, then the 0 mean flow condition is assumed. However, ID flat cannot be 0 if method equal to negative 2 or 3 or 2 or negative 2, positive 3, or method equal to negative 2 equal to 3 or negative 3, because you need to import the CFD steady solution and using IMP CFD or IMP CFD1 car through the trim flat car. The next entry is save. You have 4 options. If you say save, you will save the AIC. If you say acquire, you want to retrieve an existing file containing AIC. If you say add, then you retrieve an existing file containing the AIC and add a new reduced frequency to it. So in other words, for example, if I have a reduced frequency equal to 0.02, 0.1, 0.3, and 2, then if the AIC matrices at those frequencies are already saved, then I can say, but if I want to add additional reduced frequency, say 1, into this list, then I can say add. So ZAERO will retrieve the AIC matrices of those reduced frequencies and only compute the AIC matrix of the new added reduced frequency. And if you leave it blank, then MKLZK will not save or retrieve AIC. And for the half-span aerodynamic model, both symmetric AIC and anti-symmetric AIC are always generated together, regardless the boundary condition of the structure is symmetric or anti-symmetric. So once AIC is saved, the restart job can use either symmetric or anti-symmetric structure model solution. Because if you have half-span model, if you save AIC, the AIC has both symmetric and anti-symmetric AIC. Then when you rerun the job, but this time you change the structure boundary condition from the symmetric one to the anti-symmetric one, but you still can retrieve the AIC because the anti-symmetric AIC already exists. The file name, you specify a name of the file on which the AIC is saved or retrieved, and this entry will give you 16 columns to specify the file name. But however, if the file name is too long, and you can specify a $sign, okay, then followed by an integer, and this integer refers to the ID of a card called AIC file. And in this file, you can specify a longer name of the file. In fact, in all ZAERO input card, whenever you need to specify a file name, you always can use this option. So you start with the $ and followed by integer. Then this integer refers to the ext file card. Print option, you can print print out the various Uncity aerodynamic solution. And the last one is a list of reduced frequency. The absolute value of this reduced frequency represents the reduced frequency k, which is defined as k times omega times REFC divided by 2 divided by free stream velocity. REFC is the reference call length defined in the LZ card. And if you, because ZAERO always require a 0 reduced frequency to be listed in here, but if you don't list a 0 reduced frequency, ZAERO will automatically add a 0 frequency in the list. So if you input, you have 4 non-zero frequency, but actually ZAERO will generate 5 AIC matrices, and one of them is at 0 frequency. And the FREQ can be a negative. The negative does not mean a negative reduced frequency. The negative sign triggers the program to use more Gaussian integration points for accurate numerical integration at high reduced frequencies, because to compute the AIC, the coefficient of the AIC matrix, it involves some numerical integration, and this numerical integration using the Gaussian integration approach. Okay, if the frequency is high, then the Uncity CP will be highly oscillatory. So if you have a not so refined model, but if you want to ensure the AIC is a converged solution, then you put a negative sign, and internally the default Gaussian integration point is 5. But if you put a negative sign, that becomes 25 Gaussian integration points. So the computational time will be increased, but the accuracy of the AIC can be enhanced. And actually, saving because AIC is independent of structure. So if you want to change the structure, but the aerodynamic panel model is a set, so you can reuse the saved AIC. So however, the AIC matrix must be recomputed when the aerodynamic panel model is changed, the Mach number is changed, the input card Trin flood is changed. A new reduced frequency is specified. In this case, you want to say save equal to add. Okay, and the steady background flow for the Z-Tran method is changed. So because Z-Tran method, if the AIC is acquired, ZAERO does not process either IMP or IMP CFD1 card. Okay, so the first time when you compute the AIC using Z-Tran, you have to use IMP CFD or IMP CFD1 card. But when you retrieve the AIC generated by the Z-Tran method, you don't need to specify those two cards. The AIC matrix can be reused even when the structure finite element model is changed, and the spline input card is changed, and all the downstream aeroelastic disciplines like flutter, trim, M-load, G-loads, E-loads, nonlinear flutter is changed. So those module has no impact on AIC. So you can reuse AIC. And so reusing a previously saved AIC matrix can significantly reduce the computational time. And however, if the aerodynamic panel is changed but the saved AIC is reused, and a runtime database matrix reading error occurs if the number of boxes of the changed aerodynamic model is different from the size of the saved AIC matrix. However, if you change the model but the number of panel is the same, and ZAERO cannot detect such an error, and otherwise, so obviously you will get a wrong error elastic solution. And the modeling guideline of the MK car is that the frequency domain Uncity pressure is oscillatory in nature. The number of waves of the oscillatory pressure along the streamwise direction is proportional to the so-called compressible reduced frequency, which is the reduced frequency times Mach number divided by square root of 1 minus m squared. So you can see this compressible frequency increase rapidly when the Mach number approach 1. So the number of wave increase when k increase or Mach number approaches 1. And this is an example which is a 2D Onslay pressure distributions, and due to a plunging motion at k equals 1 and at Mach number 1.11, 1.25, and 2.5, and computed by the exact Jordan's exact theory. So if you look at the Uncity CP, if at Mach 2.5 the compressible reduced frequency is not so high, so you get a wave like this. But as the Mach number approaching to 1 and this number become larger, then you can see you have a highly oscillatory Uncity CP. So because of this oscillatory nature, convergence of solution with respect to the number of aerodynamic boxes along the streamwise direction of the aerodynamic model becomes an important consideration. And Mach number 1, the number of wave is infinity. So you can use ZSAP to circumvent this problem by solving the sonic potential equation. The non-converged generalized aerodynamic forces may contaminate the aeroelastic solution. So you have to make sure you have a converged AIC matrix. And for a good representation of the one sine wave, to capture the wave, for example, we have one wave along the core, and this core probably will need about 12 boxes, core-wise boxes, okay, and to capture this wave. So we have a criterion. So the delta x, the core-wise length of each box, must be smaller than this number. So you can see when beta is a square root of 1 minus m squared. When beta becomes smaller or Mach number approaching 1, and you need a very small delta x. And if the criterion is not satisfied, ZAERO prints out the following warning message: warning, at Mach number, this Mach number, this reduced frequency, the core length equal to this number of body or wing boxes ID equal to that is too large, and so once you have this warning message, you can either refine the model or put a negative sign in the MK LZ of the reduced frequency that will trigger ZAERO to use more Gaussian integration points and to improve the convergence. The Trin flock car is referred to by the MK LZ car, and in this car you specify the mean flow condition in terms of angle tach, beta, roll rate, pitch rate, roll rate, pitch rate, yaw rate, and the label is the control surface label. You put a value in terms of degrees of the control surface deflection. So this defines a mean flow condition, and this entry IMP CFD, it refers to IMP CFD or IMP CFD1 car to import the CFD steady flow solution for the Z-Tran method. And if Z-Tran method is selected, the entry method equals 3 in the MKLZ car, the Trin plug car must exist to import the steady CFD steady solution by the IMP CFD card. The mean flow condition at which the CFD solution is generated should match those specified by the alpha beta. Otherwise, a warning message occurs. So this alpha beta, and this is the definition of the non-dimensional roll rate, pitch rate, and yaw rate. And the input CFD imports CFD solution from a structured CFD code, because the CFD code has two types. One is called structured CFD. They use structured mesh. Another type is unstructured mesh. So you import the steady mean flow solution by interpolating the CFD solution computed as a structured mesh to the volume cell of the Z-Tran model. And the beta car plot cell can be used to visualize the imported CFD solution in the volume cell created by the cell wing, cell BDY, and cell box. Okay, those cars are used to generate the volume cell for the Z-Tran method. And once you import the CFD solution, and the Z-Tran method will interpolate the CFD solution in the flow field to the centroid of the volume cell. So you have ID CFD, which is referred to by the Trin plug car. The ID CFD can be negative. If negative, the ZAERO job will be terminated after the IMP CFD data is processed. So also ZAERO will print out the interpolate CFD solution in the volume cell. Okay, so it will give you more information regarding to the how accurate the interpolated flow is. And the trans F, because sometimes if the CFD mesh and the ZAERO aerodynamic model are located in a different coordinate system, and then you can use this Courtois car to transform the CFD mesh into the ZAERO aerodynamic coordinate. And also the trans F can be a negative integer. This negative sign implies that CFD is located in the pilot's left-hand side. Okay, so Z-Tran method can flip the right-hand side CFD mesh to the right-hand side. And the OMI CFD refer to an OMI CFD car to define a set of CFD grid points that are excluded from the interpolation. This is because the Z-Tran method requires the velocity of the CFD solution in the inviscid region. The interpolation for obtaining the steady mean flow velocity in the volume cell must exclude the boundary layer from the Navier-Stokes solution. The form CFD it tells you what kind of format of the CFD mesh and CFD solution is, and because there are various options of the plot 3D format. Plot 3D format is a standard format of structured CFD, but however, even they all use so-called plot 3D format. The plot 3D format can be ASCII or binary, or they have a so-called with I blank, without I blank. That they have various options. And CFD mesh. So it's a file name which contains the CFD mesh of the structure mesh, and and the CFD out contains the plus 3D format to contain the CFD solution, the CFD solution in the volume mesh, and and those two files we also give you 16 columns to specify the name. If the name is too long, then you can use a dollar sign followed by the integer. That integer refers to an ext file car. In the car, you can specify a longer file name, and an ID cell is an optional input to adjust the position of the aerodynamic volume cell, so that they associate the surface aerodynamic boxes overlap the CFD surface mesh, because you may have a say you may have a ZAERO model which the wing match with the CFD surface match, but the underwing store does not match. So you can use this ID cell and ID core option to locally change the position of the ZAERO surface match in order to match with the surface match of the CFD. OMI CFD, and it is referred to by the IMP CFD one car, and this because the Z-Trin method requires velocity of the CFD solution in the invis region. So in order to avoid the Z-Trin method interpolate the CFD solution within the boundary layer, so you have to exclude the boundary layer from this interpolation process. And so this one is referred to by the IMP CFD. But this one can be a negative integer to deactivate the exclusion of a boundary layer from the interpolation. And gamma is a specific heat ratio. Default is 1.4. And you have to you want output a file to specify to store the interpolate to store the ZAERO surface panel model and the CFD surface grid, so you can verify the good overlapping between those two models. And the file, the format of the file can be either TechPlot, pattern, ideas, and so on. And the files SOL, you can look at the interpolate surface CP from the CFD solution on the Z-Trin surface panel model, and so you can plot it, the interpolate CP and the Mach number. So you can use this to verify how good the interpolation is. G scale is a global scale factor applying the X, Y, Z of all the CFD grid point, and then after that you have a block I star I, I N I, and J star JN, K star KN. So in the structure mesh, you have because it can be a multi-block structure mesh. So you have to say which block, and the starting I, ending I, starting J, ending J, starting K, ending K. Within this IJK, all the CFD solution will be excluded from the interpolation. Example is that, so you have a very thin layer, a very refined mesh near the surface. That inside there are the boundary layer solution. You don't want Z-Tran to interpolate the solution from those mesh. So you can use omit CFD to exclude that. And also you can output this file mesh. So you have the Z-Tran surface panel model and also the CFD surface mesh, and so you can verify the overlapping between those two surface model. And also you can use this file SOL to look at the surface interpolate surface CP on the Z-Tran panel model and compare with the CP on the CFD surface mesh. And we also have a card called plot cell. The plot cell generates the plotting file, storing the interpolate CFD solution in the volume cell created by the cell wing, cell body, cell box Bogota card. And the example is that you have ID and ID CFD refer to IMP CFD or IMP CFD1 card, and only the tech plot option is allowed. And then you give a file name. Again, if the file name is too big, then you can specify a $sign followed by an integer. This integer refers to ext file Bogota card. In that card, you can specify a longer name. And so the plot cell card is active only this ID CFD match with the IMP CFD or IMP CFD1 card. Then you can generate a plot file which you plot the local Mach number within the volume block, and then you can compare this to the CFD solution on the CFD volume mesh. So you can verify the interpolation, and also you want to make sure that the volume block is big enough to contain all the supersonic local supersonic flow. So in this case, and in this region is the local supersonic flow. And so this verify that the size of the height of the volume block is big enough to contain this supersonic local supersonic flow. If the height of the volume block is not big enough, and you use a plot cell card, you can find out that this problem. Then you have to increase the height of the volume block. IMP CFD, just like this IMP CFD1, just like IMP CFD, except it imports the unstructured CFD. Again, you can use plot cell card to look at the interpolate solution in the volume cell, and the IDC CFD is ID, and the trans F is same as the IMP CFD. But however, unlike the structured CFD, the unstructured CFD code, they don't have a standard format. So the data will tell ZAERO what kind of format. Okay, and we have several options. If it's a data equal to plot 3D, the CFD results are stored in terms of a 5 flow variable of the Navier-Stokes and Euler equations. Rho U, rho V, rho W. This is the density, momentum along U, momentum along V, momentum along W, and the energy. If you say data equal to Fun 3D, then the CFD results are computed by Fun 3D. If data equal to CFX, the CFD results are computed by the commercial code called CFX. If data is not equal to above, then you have to follow certain format described in the in the user's manual of the IMP CFD1 car. And the CFD file, then you specify a file name which store the unstructured CFD solution, and the non-CFD, because the CFD solution can be normalized by different methods. If one is normalized for the free stream density and the speed of sound to be 1, if the 2 is normalized by the for the free stream density and free stream pressure to be 1, if the 3 is normalized for free stream density and the velocity to be 1. And for data equal to CFX, norm CFD refers to an ID of CFX param car. In this car, to specify the dimensional free stream velocity and pressure, because CFX, they don't use the non-dimensional flow quantity. Everything computed by CFX is dimensional. And X scale, and again, it's a global scale factor to apply to the XYZ of the CFD grid. Gamma is a specific heat ratio. X form is a format of the file mesh and file SOL. The file mesh, you store a mesh just like an IMP CFD car. You will output the Z-Trin surface panel model and the CFD surface mesh, and you can plot them together to verify the overlapping between those two models. File SOL, you will output the interpolated CP and Mach number on the Z-Trin panel model. Omit CFD, it refers to omit CFD1 car to exclude some CFD grid in the boundary layer from the interpolation. And ID cell, ID core, just like an IMP CFD. If you want to adjust some ZAERO aerodynamic model in order to match with the CFD surface mesh, then you can use those two options. And the omit CFD1 is referred to by the IMP CFD1 car, and this entry called level, and you specify a scheme for omitting the CFD grid. If level equals 0, the surface grid will be omitted from the volume solution, because the surface velocity computed by the Navier-Stokes solver is 0. And the form, again, only tech plot is allowed, and the file omit, and so it's a file name to store the omit CFD grid point, okay, and the file retain, again, is a file name to store the retain CFD grid. And FM fact, a real number to specify a factor. If a level equal to 1, the grid with the local Mach number being smaller than the M fact times the free stream Mach number are omitted. And then you have you can specify a region in this region, and only within this region the unstructured CFD grid are considered for interpolation. So this IMP CFD1, you can verify the overlapping between the unstructured surface mesh and the Z-Trin panel model, and then you can look at the interpolated CP on Z-Trin panel model. And also in the IMP CFD1, for example, if you have a underwing store which does not overlap with the CFD surface mesh, then you can use the Control card to locally adjust the Z-Trend panel model in order to match with the CFD surface mesh. And we have a card called RBQHH because this because the generalized aerodynamic forces of the rigid body mode actually can be they actually are related to the aerodynamic stability derivatives. Now, if you have a CFD computed or window measured stability derivatives, you can use that. You can use RBQHH to replace ZAERO computed one by the wind tunnel or CFD compute stability derivatives. So you have a ID MK, and ID MK refer to MK LZ car, and in this car computed QHH and QHC of the origin body mode will be replaced by the input stability derivatives. And step X is yes or no, because in the wind tunnel measured stability derivatives, they are in the they are in the stability axis. Okay, and for example, the x of the stability axis goes forward. The z axis go downward. So this is opposite from the ZAERO aerodynamic axis. So if the stability derivatives are defined in the stability axis, then if you say yes, and ZAERO will automatically correct the sign. Okay, and the Fugoi, if you want including the W over Q in infinity in the QHH matrix, and the gas either yes or no, you want to correct the gas or not, and the CPRH, you want to correct the Uncity pressure of the rigid body mode, and CPRC, you want to correct the unsteady CP due to control surface deflection. And the print, you can print out the CPR and the CPC before and after the RBQH is applied. And tip to tip, because if you say tip to tip, yes, all input aerodynamic stability derivatives are of the whole aircraft, the full span model. If you say no, they are obtained on the half span model. And then after that, you list out here. You specify CD, CY, CL, CR, CM, CN. That means this column belongs to the drag. This column belongs to the side force. This one belongs to the lift. This one belongs to the rolling moment. This column belongs to the pitch moment. This column belongs to the yawing moment. Then you say Trin, then this becomes CD na, CY na, CL na. If the U, it does become DCD by DU. U is the perturbation velocity. And if you say alpha, and this will be a DCL by D alpha, and or DCM by D alpha, then you input the CL alpha, CM alpha here, and then ZAERO will use the CL alpha and CM alpha to correct the rigid body sum matrix of the QHH matrix, and this is for roll rate, pitch rate and yaw rate. This is for alpha dot, beta dot, and p dot, and this is for a control surface label. And you want to correct the replace the control surface aerodynamic stability derivatives by the wind tunnel data or CFD computed data. And this is the equation. Once you import the aerodynamic stability derivatives, how ZAERO you use those to replace the QHH. Okay. And then if we want to apply the Z tau method, and if we want to use the force and moment correction method, the car is called WT1 AJJ. And WT1 AJJ corrects the AIC matrix by a force correction method, so that the force and moment computed by the correct AIC match with a given set of component force and moments. So the IDMK refer to the IDMK of MK LZ car, and because for the half span model you may have a symmetric AIC or anti-symmetric AIC, so you have to say SIM, anti or ASIM. ASIM is for full span model, and K index is index of the reduced frequency, and so you want to correct AIC of this reduced frequency, and so you have to specify a index of the reduced frequency here, and the method you can use either the steady force correction method or unsteady force correction method, and of course the unsteady force correction method is recommended. And then you can input your own weighting matrix, and then after that you have a WT1 file. You can output or input the weighting matrix, and then this is IDFRC1 refer to WT1 FRC car. And so the force moment correction method, and it is you have uncorrected AIC, and then you given a set of component loads. Then based on this become a constraint function, and you compute the WT1 weighting matrix. So WT1 times AJJ becomes the corrected AIC. Okay. Then the WT1 FRC actually lists out the component loads. Okay, so because we, for example, the component loads is for say wind rule bending moment. Actually, we need the slope of the bending moment with respect to some sort of mode. Okay. And the typical example is that we have a type equal to FEM, the structural finite element model that are imported by the assigned FEM. A sub Z is a control surface. Low mod is defined by the low mod car. Region is for rigid body. Then the label, you have many different type, and then low mod car, you refer to a low mod car, and in the low mod car you define what kind of component load it is, and then you have a dynamic pressure if the component load is measured in the wind tunnel. So at that what kind of dynamic pressure condition you measure the component loads, and then the WT1 FRC require you to input the A1 and the R force 1. That's the real part
of the component loads and imaginary part of the component loads, and you have A2 as another factor, and then the component loads. So the F given is defined by A1 times the R force 1 and plus I force 1, and plus A2 and R force 2 plus I times I force 2. And for instance, if those two component loads are the hinge moment of a control surface at angle theta 1 degree and 0 degree, so A1 should be 180 divided by pi. A2 will be negative 180 divided by pi. So the F given is the slope of the is the derivative of the component load with respect to a unit change of the say angle theta. If you want to use a downwash weighting matrix, the car is called WT2 AJJ. So again, you have a refer to MK ARZ car. You have a symmetric, anti-symmetric, asymmetric type, and you have label, K-index, method, WT2 file. Then you have a form either DMI or CFD to specify the form of a given pressure coefficient. Then you specify this one refers to IMP CFD or IMP CFD one car, and if the form equals to CFD, and this at the one at the angle tag, and this A2 is another angle tag, and this is referred to another IMP CFD or IMP CFD1, which contains the CFD computed solution. Then WT2 AJJ will calculate the DCP by the alpha and using this equation. So if this one is computed at alpha equals 1 degree, this guy is computed at the angle theta 0 degrees. So A1 should be 180 divided by pi. A2 should be negative 180 divided by pi. So WT2 AJJ using the finite difference to calculate the DCP by d alpha, say. And WT UCP, you correct the unsteady pressure by the weighting matrix approach. So you only correct a particular the unsteady pressure of a particular mode, and so in other words, you don't correct AIC, you correct the unsteady pressure of a particular mode. If this mode is a control surface mode, so we suggest you to use WT UCP, and to correct only the control surface mode. And so you leave the unsteady pressures of other modes untouched. Finally, you can use CP to plot unsteady CP.